Okay, and number 3. So number 3, projections just in general, right? So I was good with kinda, like,
Yeah,
figuring
projections are
out the other
tough.
stuff. Yeah, this one I just did not understand from the
Yeah,
core of it.
projections are tough, and they every single time it feels like it takes me a moment or two to figure it out again. But okay, so how do I want to put this? I can spit. So there's almost certainly going to be a formula for you in your textbook that tells you how to do a projection of one thing
Right.
onto another.
Yep.
And then if you wanted to, you could just look up what that formula is and just plug it in to get the answers. But I'm not going to concern myself with the specific values of X and Y. I'm going to sort of go through the idea and try to explain why the formula is what it is. Is that
Okay,
reasonable?
yeah, yeah, no,
Right?
that works perfect. That is exactly what
Right.
I need.
So I think that, in no way does this constitute giving you the answer because I'm not doing it for
No.
your specific, I'm providing you with a textbook already is, but I'm hopefully explaining it in a way that's more digestible.
Yes,
So
that would be great.
a projection, right, of uh let's say X onto Y, right? What this is saying is, let's say this is basically saying of when you project X onto Y, that's sort of like saying Y is the ground, right? That's like I'm going to try to use a real world analogy here of light coming in from the sun, and projecting a shadow onto the ground. And the idea here is that the ground here, the one that's being projected onto is the ground. So like if you literally just imagine this as like, um, if you literally just imagine this as like the ground outside your house, that's Y. And then there's going to be beams of light coming in perpendicular to Y, right? This is the sun's rays. They come down in a straight line. And the sun's rays, let's say that X is like a tilted beam that's just at an angle for whatever reason. And it's going to cast a shadow of whatever length, right? And this right here is the projection. So the projection is the shadow. So like just not mathematically, but like just visually in the real world, can you understand what we're talking about right now?
Yeah, no,
Yeah,
I see that. Yeah,
right. Like imagine this is like your house or something, right? And
right.
you're leaning a ladder against it or something, and you're trying to figure out what the let's say that the height or the length of the ladder, or the if you treat the ladder as a vector, the components of the ladder vector, but you're trying to figure out how long the shadow is, right?
Right,
That's what this
right.
question is talking about right now. Does that
Okay,
motivation make sense?
it does. Yeah, that kinda gives it a frame. Yeah.
Right. So what we're gonna say right now is okay. So the goal is to find the projection, right? The goal is literally to find a vector that stands for the projection, right? And that means finding the three components. So instead of
Right.
like shading it as a squiggle, I'm going to represent it as a line, or sorry, represent it as a vector. And note by like literally by construction, the projection vector is parallel to the y vector, right?
All right, right,
Because like we're looking for the shadow, like the along the ground, which is I literally said it along the ground, right?
right, which
So
is the
it's
one.
parallel to y. That shouldn't be too surprising.
No, not
So
at
the
all.
idea here is we want to figure out what this is, and we're going to have to use the dot product, and we're going to have to use trigonometry. So buckle up. Okay.
Right, I did figure that's where yeah, I did
Yeah.
figure we're gonna
So I'm going to remind you the definition of the dot product, A dotted with B, right? There's sort of two equal ways of looking at it, which is uh, A1B1 plus A2B2 plus A3B3, right? Where A1, A2, and A3 are the XYZ components of A and correspondingly for B, right?
Right,
Right. But this is also equal to, what was it, A, the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle between the two.
right.
I'm being a little silly. I don't know why I called it A and B. I should just call it X and Y, just to keep the definitions consistent with our problem. Okay.
Okay, that's fine.
Right. So there's two separate ways of looking at this, and we're going to exploit the fact that this dot product has basically two different definitions. And you'll see what I mean in a moment. X3, Y3. So let's put it this way. What we want to find, just by basic trigonometry, is... Okay, so this is the vector x itself, right? This is the vector x itself. But if you think about this as just like a right triangle, and this is going to be a right triangle, because like by definition, the rays are coming perpendicular to the ground, right? So the idea here is if the x, this is a right triangle, you know, the magnitude of x is the hypotenuse. Right. And the value that we want to find is this one down here, which is, by definition, it's going to be cosine theta times the magnitude of x. And this is just trigonometry. I don't know if maybe you're rusty or maybe you're on top of things, but I'll just put this as a reminder, right? This is what we're trying to find, x cosine theta. Gotcha. Hopefully nothing seems Greek or foreign so far, right?
No. And I'm fairly good with trig. It's just, you know, maybe a few definitions here and there that
I gotcha. So basically, we know what x is. We know the value of x because we're literally given it, right? And we could find the magnitude if we wanted. That's just the distance formula. Do you remember that?
The distance formula is the root of something.
Yeah, like I'll just remind you that the absolute value is just the square root of x1 squared plus x2 squared plus x3 squared.
Right. Okay.
Right. So this is just so I'll just remind you what we know. Actually, maybe I'll write this a little bit off to the side just to make more room for it. We know what x is, the absolute value of x is. We know what y is. And we know like the literal vectors themselves, right?
Right.
And WTF means we want to find.
That's not what WTF means.
Okay, sure. For math, WTF means want to find. The answer we want to find, well, we said it was x cosine theta, right?
Right.
And because we literally already know what the absolute value of x is, that means that just cosine theta is what we need to find, and then we're done. Right? And the idea is, unfortunately, we don't have a protractor in this kind of abstract mathematical problem.
Yeah.
So we need to figure out theta, or cosine theta, rather, using the dot product. Yeah?
Okay. Yeah.
So this is what we know, and this is what we don't know. So here's what I'm going to say. This is the expression for the dot product. We know what x dot y is, right?
Right.
Because we know what x and y are, and we can just dot them together. We know what x is, and we know what y is. Well, like, shoot, right? If we know everything else and you just need the cosine, or rather the x times the cosine theta, we just divide through by like y and we're done. But like, okay, so this basically just tells us the magnitude, right? And remember that to actually find the vector, we need to have both magnitude and sort of the direction. So that's a little bit of detail that I needed to quickly look up to remember, but honestly, it's not hard. Sure. So basically, this was the magnitude, right? We said x cosine theta was the magnitude of the shadow of the projection.
Yeah.
And that's just x dot y over, what was it, the absolute value of y?
Right.
Right, that's just literally just moving this over here via division.
Yep.
Right, and remember, magnitude, literally a straight up number. Literally a straight up number. But the question is asking for a projection, which just by their definition is a, what do you call it? Projection, which is a vector, which means it's a magnitude and direction. So the idea here is that, well, if we already know the magnitude of this thing, right, and we know that it's parallel to y, let's just grab the information, let's just grab the unit vector information of y and multiply it by this. So this becomes our scalar, and you know, the scalar with the magnitude, and the direction is just y, the vector, divided by its own magnitude. Do you see that?
Can you run through that a little slower
for
me, just so I can?
Of course. So to get the direction, are you familiar with the idea of a unit vector?
Yeah.
Right. So a unit vector of any vector, including for our particular example y, is just y, the vector, divided by its own magnitude.
Right. Okay,
right. So this is sort of the direction information.
Okay.
Right. And all I'm saying is to get the final information for the projection vector, you just take magnitude and you multiply it by direction. You see
Okay,
that?
the x.
Like this is
Yeah,
a straight up number, right? This is kind of like k.
right.
You know how all the time we had like k times x, right? This is the magnitude, and
Uh-huh.
this is a vector that just happens to have magnitude 1,
Okay.
right? All I'm
Yeah, I
saying
see
is we're
that.
just slamming these two things together and multiplying them to get
Okay,
x
yeah,
dot y.
I get it now. I'm tracking. It
Gotcha,
took a
gotcha.
little
That's
second.
awesome. So then this y over here, and then there's going
Yeah,
to be a, so the x dot y comes from the magnitude. Why is my
right,
screen? The y over here comes from this thing over here.
right.
And then on the bottom, because there's a magnitude of y on both of the denominators, it's just going to be
Yeah.
magnitude of y squared,
Okay.
which
Yeah.
might be confusing for just a brief moment. But remember that once you take the magnitude of y, at that point, it's literally just a number. So you can square that number just fine.
Right.
Right.
Which
And
is different than the I stuff and that, right? I
yeah,
do
like
know.
you could think about like, you know, there's no reason why you couldn't call a, I cross I, you know, you
I
could call
squared
that like
and
I squared under the cross product, but that just seems overcomplicated because it's 0 anyways.
and ask him for trouble too,
Yeah,
right?
right,
So
right.
okay.
But
Yes,
like
no,
the
I'm
dot
tracking.
product, notice that this is actually the notion of the dot product squared just fine.
Right.
Right? Because y dotted with y itself is equal to y squared.
Right.
Do you actually know why that is?
No, not for
Okay,
the
let me just demonstrate the equivalence, right? So we said earlier that the absolute value of y is equal to, well, I'm just writing out y1 squared plus y2 squared plus
okay.
y3 squared,
Yeah.
right? So that means that the absolute value of y squared, well, you just get rid of the square root signs, right? y1 squared plus y2 squared plus y3 squared.
Right.
Yeah?
Yep.
So y dot y, literally, if y is y1, y2, and y3 dotted with itself, y2 and y3, that's literally equal to y1 squared plus y2 squared plus y3 squared. Literally the exact same thing,
Yes.
right? Like, what a coincidence. What are the odds of that? Surely, of course, the real answer is, I'm sure the mathematicians who define this stuff contrived the dot product, based on what was useful and sort of based
Yeah.
it off of the idea of magnitude or distance. Or sorry, how to compute like the magnitude of a vector, which comes from Euclidean distance.
Okay.
Euclidean distance is basically just this thing right here, saying the magnitude of a vector is each of the components squared. You add those up and take the square root.
I see.
Yeah. But okay, so at this point we've justified why the projection vector is what it is, right?
Right.
It's this thing. So when x gets dotted onto y, and it's one of those things where I'm hoping that you could follow every step of the way, but you might still find this like final product kind of intimidating when you see it all meshed together.
Yeah,
Yeah.
which is why really
Yeah.
important that I divide this up into like
Sure.
pieces and
Well,
figure out
take it
how
a
to
step at a
chunk it.
time. Take it a step at a
Right.
time, right? Take it a step at a time and figure out what literally x dot y is. Figure out what y squared is, which again is y dot y. Is probably the easiest way to think about how to calculate it. And then just once you have those two things together, x dot y divided by y squared is literally just a scalar number. And then just multiply that by whatever y the vector is, and you're golden.
Okay.
Right? So take it a piece at a time. You
Right.
see that?
I mean, I do see that. Yep.
Mhm.
I'm writing down some of
Sure.
the steps.
I mean, would you like me to go through just a sample computation
Yeah,
for the
that
heck
would
of
be
it?
great. Yeah, no, that'd be
Sure.
really
So I'll
great.
just choose two like pretty random
Yep.
vectors, okay?
Yeah, yeah,
And I'll
great.
make sure that they're not the same thing as, okay, just to do some like two random x is equal to, I don't know, 1, 2, 3.
Yeah.
Just no, maybe just the simplest example I can think of.
Yep.
I don't want to choose two huge numbers, but like maybe call it like 2, 3, 4.
Yeah.
Okay. So I'm literally just using this thing over here, right? Using these expressions. So the projection of x onto y. Like literally just plug them in. So what is x dot y? The first part is just 1 times 2 plus 2 times 3 plus 3 times 4, right?
Right.
And then what the heck is y? Y itself is just this vector. Is it okay if I just write it like 2, 3, 4 vertically with
Sure.
brackets
Yeah.
to let you know that it's a vector?
Yeah. Too easy.
Okay. And then on the bottom is just y dot y, which is 2 squared plus 3 squared plus 4 squared.
Right.
Right.
Makes sense. Yep.
We can do the computation together if you want to, but this is literally a number,
Nah,
and that's
that's too
divided by
easy.
literally another number, and then you just multiply, each, you multiply that through by 2 to get the x value, multiply that through by 3 to get the y value, and so on and so forth for z value. Like, do you want me to
Okay.
carry through this to the end just for the sake of
Nah.
being concrete?
I mean, only if you want to, but I'm really good at this point. This was enough broken down steps, but
Okay,
yeah,
sure.
it's up to you because we are running out of time.
Oh
Yeah.
yeah, sure. Well, okay. Got a number of problems done. I could cut this up the way we talked
Did-
about. When you see sines and cosines, just keep a couple of identities in mind. The most useful one is
I'm sorry, not for. Oh, I'm just talking about for all the homework problems, right?
yeah, sure.
Because we were going to work on something. You said maybe tomorrow, right?
Hmm. Yeah, I mean,
So I don't think we're going to get through all the problems, but it would be helpful if you saw a couple that I could look at ahead of time to make sure I'm tracking ready to go.
okay. Um,
But if you hadn't had a chance, you could just maybe just hit me up
sure.
on
I
message.
just as a very brief glance, when they ask about when you have two vectors and they ask
Yeah.
whether the angle is acute, obtuse, or orthogonal, right?
Right.
You got to remember to use this identity right here. I mean, it's the definition, but it's super useful, right? It's
Right.
when you have two vectors, you can literally calculate x dotted with y. You can
Yes.
calculate the magnitudes as well, and that'll tell you cosine theta. And then
Okay.
because you can just do arc cosine, that'll let you figure out what theta is. That'll let you tell whether it's acute, obtuse, or orthogonal.
Right. Okay. All
Right.
right. That actually is very helpful to scope
And in
that.
fact, even a shortcut is if it turns out that x dot y is 0, you know right away that it's orthogonal. Right? Because the
Oh,
dot
right.
product,
Yeah. Of course.
right,
Yeah. Okay.
tries to maximize the value when they're parallel. So for the dot product, when you have two things, it's maximizes the dot product. But if
Right.
you have two things over here, A and B, then A dot B is equal to 0 when they're orthogonal.
Right.
Orthogonal. Okay. But
Yeah.
maybe take a look at a couple of those on your own, and hopefully find it reasonably productive.
Yeah. No,
Yeah.
this was very helpful. This got very very helpful. I
Yeah.
really appreciate
No, I
this.
definitely am experimenting with the format and hope to make things, even more streamlined as time goes on. And happy
Sure.
to, invite more people, do things in groups.
Yeah, I would love to help you work out the process until you get it where you want. So this is helpful for me too while we're doing this.
Sure thing. Okay. Well, take
Okay.
care.
All right.
See
Take
you.
care. I'll just hit you up and see what works best for you
Yeah, I'm
tomorrow.
pretty much free all of tomorrow.
Okay.